Hello and good day everyone. My name is Ahmad Shafi bin Salihin. Today, I will be presenting my FYP title of Development and Characterization of Activated Carbon from Agricultural Waste. My supervisor is Dr. Liu Wailon, and without further ado, let's begin. Activated carbon is commonly used as adsorbent for purification, separation, and extraction process in the industry. This is due to its characteristic large surface area, high degree of porosity, and high surface reactivity. Commercial activated carbon commonly produced from non-renewable and non-environmentally friendly materials such as bituminous coal. Agricultural waste was not fully utilized of its potential in Malaysia and also facing a problem with its disposal management. The agricultural waste that was used in this study is palm kernel shell and rice husk. This is because of it is low cost and the amount of this agricultural waste is abundant due to its availability in Malaysia. It is renewable and also environmentally friendly. Moving on to the problem statement. The first is the agricultural waste production increasing as the number of population increase, and this could pose a serious risk to the environment. The second is to diversify the usage of activated carbon in the agriculture sector. And lastly is the commercial activated carbon is considered costly. Next is the objective and the scope. The first one objective is to provide comprehensive foundation of activated carbon from rust husk and palm kernel shell. The second one is to identify the characteristic of activated carbon based on the surface area, pore-size distribution, surface morphology, and the functional group. The first scope is by doing literature synthesis from different literature based on the chemical and physical activation of activated carbon. Next one is surface area using PET method, Fourier transform infrared analysis for the functional group, and scanning electron microscopy for the surface morphology. Then we move to the methodology. Since these researchers cannot do experiment, first thing first is the source and searching. Getting research articles from different sources such as Scopus, Web of Science, and Science Direct. The next part is reviewing the article and doing literature synthesis. After that, we'll be getting characteristic of activated carbon and proposing the conceptual framework. For the characterization of activated carbon, we'll be looking at the bed surface area using nitrogen adsorption isotope, FTIR analysis for surface functional group, and SAM analysis for surface morphology. Physical activation refers to carbonization is followed by the activation of resulting char at elevated temperature in the presence of suitable oxidizing gases such as carbon dioxide, steam, air, or their mixture. For chemical activation, carbonization and activation are performed in a single step using chemical agents such as potassium hydroxide, sodium hydroxide, zinc chloride, phosphoric acid, and etc. As we can see here in the table 1 for rust husk activated carbon. Potassium hydroxide as activating agent giving large surface area compared to the other activating agent. During the carbonization, potassium hydroxide is reduced to metallic potassium. It is believed that when the activation temperature reaches the boiling point of K around 750 degrees, potassium diffuses into the carbon layer and causing new pores to form in the carbon structure. As for zinc chloride, we can see that the surface area is the lowest among other activating agents. It's because of the presence of silica that prevent the penetration of zinc chloride into the carbon during the activation. To avoid this, it's suggested that the process undergoing pre-treatment to remove silica content by doing acid leaching or basic leaching. Next for pumpkin shell activated carbon. Here we can see that zinc chloride is activating agent giving the higher surface area compared to the other activating agent. This is because the silica content in the pumpkin shell is lower than rice husk. It can be said that chemical activation gives more surface area compared to physical activation. For physical activation, steam is mostly used as the activating agent for both agricultural waste. The surface of activated carbon using physical activation is related to the activation temperature. The higher the temperature, in the range of 900 to 1100 degrees Celsius, the larger the surface area. However, the yield of the activated carbon would be low. Based on the result, the activated carbon for both agricultural waste pose mesopore and micropore structure in the carbon. The mesopore structure is in the range of 2 to 50 nanometer. From the FTIR analysis, OH, CH, C double bond C of aromatic is most likely to be found in the resource activated carbon. OH group indicated that water are chemically absorbed from the activated carbon and form hydroxyl. The OH, COC, C double bond O group are likely to form from the corrosive effect of potassium hydroxide on the porous carbon network. C triple bond C cannot be found in activated carbon by steam activation, but can be seen in CO2 activation. This might be the appearance of ketone group during the CO2 activation process. Also can be seen the silicon functional group in the rice husk activated carbon. They show that the rice husk containing silica. For the palm kernel shell activated carbon, it is same like rice husk activated carbon, also containing OH group and others group as can be seen in table 4. More peak detected on FTIR analysis showing that palm kernel shell activated carbon has many functional groups compared to rice husk activated carbon. Based on the both table 3 and 4, chemical activation activated carbon giving more functional group than physical activation, except for activated carbon using activating agent of N2 over air. This process of N2 over air called is two stage of physical activation. In this slide, the figure shows the surface morphology of rasa activated carbon. Rasa activated carbon with sodium hydroxide activation showing a honeycomb-like micropore structure. This shows that using sodium hydroxide as activating agent give a well structure of activated carbon. Sodium hydroxide erodes the carbon surface to form pores during the activation process. As can be seen in the figure 2 with 2H activation, the process is the same like sodium hydroxide activation. The reaction with carbon create the pore and widening the existing pore. Figure 3 show the raw pumpkin shell. We can see here there is no pore in the raw material. During carbonization, it creates amorphous layer and some pores. During activation process, a well-structured pore can be seen as in figure 4. Potassium hydroxide removes the volatile compound that could hinder the formation of pore. For figure 5, there is some cavity. We can see it shows that some of the volatile compound was not fully removed during the steam activation. The combination of continual devolatilization of volatile compound and carbon H2O reaction occurred due to the presence of steam in the activation gas, which is led to the formation of pores. As a conclusion, rasas and pumpkin shell has the potential to use as precursor for production of activated carbon. Chemical activation giving Rust activated carbon and pumpkinner shell activated carbon a much higher surface area, more functional group that exist in the surface and well-developed pore structures compared to the physical activation. And this study provides more information about rust and PKS as activated carbon. That's so this is the list of reference used in this presentation. Thank you for your attention.